I'm going to change the radius of the circle. I'll just make it a bit smaller because it's all too big. And move C to change the position of the tangents. Now, girls, both CE, can you see CE along there? And CD are both tangents to the circle because at E, we only touch the circle at one point, and at D, we only touch the circle at one point. So the tangent to a circle from C to E and the tangent to the circle from C to D, what I'm going to do, we're going to show the tangent intercepts. So that's CE is a tangent intercept, don't worry about that, but the length of it is important. Now look at the length from C to E and the length from C to D. What are they? They're the same. So I'm going to move C. As I move it, it's always equal. So if two tangents are drawn to a circle from any external point, the lengths of the tangent to the circle are equal. So here's the theorem. Tangents to a circle from an external point are equal. Nice and easy, isn't it? Now, I will do the proof for this in the video this afternoon or tonight, whenever I get time. All right? So tangents to a circle from an external point are equal. Christy, this video is for you. Everyone else is here today. We have 24 people. I know, now I can't use it again. So, it doesn't matter. I'm too tired. I'm going to make mistakes. I'll probably make mistakes tonight too because I've been going to bed after midnight, every night for the last 3 nights, and I'm tired. Who's going to titration comp tomorrow? They want me to go. So tangents to a circle from an external point are equal. The proof will come tonight. We done? Yay? Stephanie, you done? Yeah. All right. Wasn't going to do, but I'll do it. This is circle theorem 15. You may as well write it. Now, girls, that bit in black up the top is not the theorem. So two circles touch if they have a common tangent at the point of contact. That's not the theorem. That's just a bit of information. So, see those two circles here? That big circle and that little one, if they touch, that tangent will be a tangent to both the circles. Does that make sense? So two circles touch if they have a common tangent at the point of contact. Now the theorem is circle theorem number 5. So if two circles touch, you should be able to draw a tangent between the two circles. And that tangent will be a common tangent. It'll be the tangent for both the big circle and the little one. Now, don't worry about this internal, external contact yet. Circle theorem 15 is when two circles touch, the line through their centres passes through their point of contact. Sorry, that backslash shouldn't be there. So I'll just fix that. Now, the point of contact of the two circles is point A. That's where the two circles touch. So the two circles touch at A. That's the tangent through A. So when two circles touch, the line from the centre of the one circle to the other will pass through that point of contact, which is A. That's the theorem. Now, the alternative wording to this theorem, so when two circles touch, the line through their centres passes through the point of contact. A is the point where the big circle touches the little circle. So that's called the point of contact, okay? Through their point of contact, okay? In other words, if you draw a line from the centre P to the centre O, it'll pass through A, which is the point where the two circles touch. When two things just touch, they only touch at one point, and A is the point where they touch. Now, the alternative wording is when two circles touch internally or externally, just write it down first, the two centres and the point of contact are collinear. In other words, they lie in a straight line. Now, I'm going to show you internal and external contact. I'm going to move P, watch. Watching? Internal contact. Okay, so the one circle's inside the other and they're touching, the point of contact is A, but that's internal contact. And this is external contact. So external contact is where the little circle's outside the big one, and internal contact is when the little circle is inside the big one. But they've still got the same point of contact, which is point A. So the converse, not the converse, but the alternative wording is when two circles touch, either internally or externally, the two centres and the point of contact lie in a straight line or are collinear. Okay? So in other words, those 3 points lie in a straight line. You want me to put it back in? Oh, all right, no worries. Why? Oh, okay. And see, we can move, change the size of the circle.
Can you change the... Oh, wait, no, jokes.
I can change the size of the circle. I can change the radii. I can make, do you want me to make P bigger than, see?
Yeah,
That'll
like
work.
that.
Yeah, that works. And I can bring this one out. Oh, no. It's programmed to keep one of them there.
Also, the circles have, one circle has to be bigger.
Yeah, yeah. Oh, it would work for 2 identical circles.
So
Yeah.
basically this theorem is like proving the 3 points
Are collinear. Yeah, that's what it's doing. Okay, I'm going to pause the video. Okay, circle theorem number 16. Notice the pink angles. The angle between, see, this is a tangent. The red line is a tangent and CE is a chord. It's not a secant because it only goes from one point of the circle to the other. So CE is a chord, not a secant. Do you get that CE is a chord?
Yeah.
Now, the angle between the tangent and the chord, that's 52 in pink, is equal to the angle in the alternate segment. See, this chord CE subtends angle CDE in that alternate segment. See, this chord CE forms 2 segments, the minor segment here and the major segment over there. So this angle is formed in the alternate segment to where this 52 is. That's why it's called the alternate segment. So the angle between the tangent to a circle and the chord at the point of contact, so it's that pink angle there, is equal to the angle formed in the alternate segment. Now this is the same segment here, that's the alternate segment over there.
So basically the opposite interior.
Yes, but you don't say it. Yeah, you just say is equal to the angle in the alternate segment. Reason, this is the segment that the 52, the original 52 is in. This is the major segment, so it's the other segment, the alternate segment. The alternate, because CE divides the circle into 2 segments. This segment where the 52 is in, and this other segment where this other 52 is in. So the angle between a tangent to a circle and a chord at the point of contact, or through the point of contact, is equal to the angle in the alternate segment. Now, this theorem, you can look at it 2 ways. Look at the green ones. Here is a tangent as well, and there's the angle between the tangent and the chord, and it equals, see, the chord subtends that other angle. So that's why the 65.5 in green is equal to this 65.5. So again, the angle between this tangent and this chord is equal to the angle formed in the alternate segment. And it's formed from that chord, but in the other segment. Okay? And I can move this around. All right, as long as this angle is formed in the other segment. Now watch if I form the angle in the same segment. It won't be the same. Now I'll just change the size of that to make it a whole number. So watch. See how 64 is in the other opposite segment to where this 64 is? If I bring it around here, it's now in the same segment. See how the pink ones aren't equal anymore? 64 and 116. But once I cross over into the other segment, it becomes 64. See? They're not equal because it's formed, that angle is formed in the same segment.
You have to change the tangent.
No, that's still the angle between the tangent and the chord, but it's not equal to the angle formed in the same segment. It's only equal to the angle formed in the other segment to where this is. See, the 64 you could say is crossing over into this segment. It's only equal to the angle that's formed over there in the other segment. Now notice this 64 here as well is equal to, yeah, but I should have made them slightly different, so I will move it. All right, we go just slightly different. Okay, angle between this tangent and that chord DC. So look what's standing on chord DC in the other segment, and it's that angle there at E. So notice that there are 2 pairs of equal angles that you can see. Now, the alternative wording is the angle between a tangent to a circle and a chord through the point of contact is equal to the angle subtended by the chord in the alternate segment. You don't have to say that. You can just say is equal to the angle in the alternate segment. Okay? Girls, you've got a lot of learning to do. In the other segment. Alternate means the other segment. Do you understand that 60... Right, look, watch. Okay. This is a chord. Yeah, I'll pause it. Got it down yet? Okay, so last theorem now, circle theorem number 17.
Is your favourite one?
Nah, I like that one. I like number 16. 16 is my favourite because it comes up so much. Got to know that one.
So basically, love number 16.
Yeah, you need to know that, and your cyclic quadrilateral stuff, need to know those. Okay, girls, this last one is here. And here it is. Okay, theorem 17. Right, Linda, P-A, Lydia. PC is called, what is it, a chord or a secant? PC. And PA is called a tangent, and you can see it written there. So girls, P, because A only, if I continued A along, it would only touch the circle at one point. PA is a tangent, PC is a secant. So P is an external point, it says PA is a tangent, and PC is a secant. I've written it down the bottom in purple. PB, girls, now this is where people get confused with this theorem. PB is a secant intercept, and so is PC. So you've got to go from P to B and P to C. I don't want PB and BC. I don't want it like that. The secant intercepts, the intercepts of the secant are from the beginning of the secant to the first bit where it cuts the circle, PB, and from P to C where the beginning of the secant cuts the second part of the circle. So I don't want to see PB times BC. I want to see PB, that's a secant to intercept. Where does the external point touch the circle? And where does the other external point touch the circle on the other end? So the secant intercepts are PB and PC. And the tangent is PA. Now PB is not a tangent because if I kept drawing the line through B, it would cut through the circle. PA is a tangent because if I continued the line past there, it would not go back through the circle. A only touches the circle at one point. Like if I draw the line from P to A and continue along here, it won't cut through the circle. But if I draw the line from P to B and continue, it will cut through the circle, so PB is part of the secant. So the rule is that PA, now I've just down here, PA times PA is 80.19, and PB times PC is also 80.19, and we can try that. Remember, these are rounded off, but if I do 7.58 plus 5.93, I get the length of PB, which is 13.51, and if I times that by 5.93, I get 80.1. It's a little bit off. 80.11 I get, but remember they're rounded. So the rule is PA squared equals PB times PC, and you need to put it in words, but the square of the length of the tangent from an external point, see, P is an external point, so you do PA squared, you do tangent squared equals product of the secants, product of the secant intercepts, equals the product of the intercepts of the secant passing through that same point.
Wait, so the 7.58 is not BC?
No, yeah, but it's not BC. You need to do PB times PC.
Yeah, so PC would be 5.93 plus 7.
That's right. PC is 5.93 plus 7.58. Okay?
Is it the most wordy part of maths?
I know, it's very wordy.
But is it get any wordier than
Oh no, that's it. So, everyone got that down?
Now I have to remember it.
Now you have to remember them. What I should do, I think I've got a document with them all in there. I should put it up and you've got to give me the wording.
Let's say hi to Christy. Hi, Christy.
Everyone's saying hi.
Did you type it wrong? PA was PB. Shouldn't it be BC?
No, it's not BC. That's what I've been saying. It's not BC. It is PC. So it's PB times PC.
But you have to add them together.
You have to add them together. Please don't do that one, because that's in the other theorem.
Yeah.
You know, well, it's off by 0.0.
It's like off by 40 something.
No, you're doing the wrong numbers.
No, it's PB times P times.
And what's PC?
Oh, I have to pass it.
Yes.
I
Girls.
hope you feel better, Christy.
Yeah, everyone hopes you feel better.
Never do your
All right. Has everyone, she better. Right. Has everyone got this? I'll just put up. Why isn't it coming up? Okay, Christy, this is circle theorem number 13. I didn't turn on the video till after this. Shh. Christy's just going to get this one. Circle theorem number 13, you can copy this down as well. So I'm moving C so that we have a tangent. So CA is a tangent to the circle and OA is the radius. And the angle between a tangent and a radius through that point of contact is a right angle. And there's your converse theorem. The line perpendicular to the radius at the point where it meets the circle is a tangent to the circle at the point of contact. You can pause the video and just write that down. Circle theorem 13. Bye.